last time what we did is characterize the ideals that give us a field when we take a quotient, right? So remember, it went like this. So R mod I is a field if and only if I is maximal. Right? So maximal ideals correspond exactly to those quotients that give you fields. We can ask a related question. Right? If we relaxed this condition and said, well, okay, maybe we don't need to have a field. What if we just want an integral domain? Right? Then, what's the condition that we need here to guarantee that we get an integral domain? Okay, so let's just attack that question directly. So let's let R be commutative with unity, and suppose that R mod I is an integral domain. Okay, so what does that mean then? So then, whenever, so let's say it like this, AB plus I, that's the product A plus I times B plus I. So whenever that is equal to I, one of these two has to be the identity, which means either A is in I or B is in I. So whenever A plus BI is equal to I, A is an element of I or B is an element of I. Can't have zero divisors. So let's sort of say what that tells us about I. So I must have the following property. And let me just put a star around this. So if AB is an element of I, then A is an element of I, or B is an element of I. Okay? So if you're going to have an ideal that gives you a quotient that's an integral domain, then you've got to have this property right here. What about in the reverse? What about in the reverse direction? So now, so let's say conversely, suppose I is an ideal, such that the quotient is an integral domain. Oh, whoop, sorry. I just did that, sorry. So such that, an ideal, I was just about to repeat myself. So suppose I is an ideal satisfying property star. Okay, so no matter what, when we have a product of two elements in I, then one of the two has to live in I. So then, in the quotient, if we have a situation where A plus I times B plus I is equal to the identity, the trivial ideal. I shouldn't say trivial ideal, the trivial coset 0 plus I. Then what does that mean? Well, then A, B is an element of I. And so that means that A is in I because of this property. So A is in I or B is in I. So this, or it follows that A plus I equals capital I or B plus I equals capital I. So if I satisfies this property, And then we take a couple of cosets, we multiply them, we get the identity. Because of this property, it forces us to conclude that one of those two cosets, one of the two factors here, had to be the identity in the first place. In other words, if I satisfies property star, then R mod I is an integral domain. We just proved something, right? The quotient is an integral domain if and only if the denominator, I, satisfies property star. Let's give, in fact, yeah, so let me just say it. So therefore, R mod I is an integral domain. Ideals that satisfy property star, they have a name for them. So let's let R be commuted with 1. So let's let R be, oh, actually I don't need 1 here, commutative. We can define this in general. So commutative, a proper ideal I is prime if for all A and B in capital R, A is an element of I or B is an element of I whenever the product is in I. In other words, an ideal that satisfies property star is called prime. And now we proved, let's collect this as a theorem. All right, we've already proved it though. So the discussion above, or in the discussion above, we proved, and this is going to be theorem 27.5, I think. 27.5. So let's let R be commutative with 1 and let capital I be a proper ideal. Then R mod I is an integral domain if and only if I is prime. One thing to note here, so we can define prime ideals as long as R is commutative, right? So I don't need unity to talk about a prime ideal. However, in this theorem, right, if we're going to have an integral domain, then we have to start off with a commutative ring with 1 so that R mod I has 1 as well, right? Remember, an integral domain is a commutative ring with 1 that has no zero divisors. So let's look at some examples. So in Z, the ideal generated by 2 is prime. So why is that? If A, B is an element of the ideal generated by 2, then What does that mean? That means that a times b is a multiple of 2, which means that 2 divides a times b. So then 2 divides a times b. But according to Euclid's lemma, that means that 2 divides a or 2 divides b. So it follows, right? 2 is prime, so it's got to divide one of those two. So 2 divides a or 2 divides a or 2 divides b. And so what would that mean? Well, if 2 divides a, that means that a is a multiple of 2, which means it lives in here. If 2 divides b, then b is a multiple of 2, which lives in here. And so 2 is an element, no, not 2. A is an element of the ideal generated by 2, or b is an element of the ideal generated by 2. However, all right, so still working in the same example, so we're still in Z. We can say, however, the ideal generated by 4 is not prime. Why is that? Well, 2 times 2 is an element of the ideal generated by 4, but 2 is not in the ideal generated by 4, right? So we have a product of elements living inside the ideal that's not contained in, but neither of the two pieces, right, to the two factors is not in there. Alternatively, so here's, I showed these both directly, so I could do this, so continuing in the same example, alternatively, we could use the theorem that we just had. So Z mod ideal generated by 2 is isomorphic to Z2. This is a field. Since Z2 is, well, it's a field, which means it's an integral domain. So since Z2 is an integral domain, ideal generated by 2 is prime. While Z mod ideal generated by 4, that's isomorphic to Z4, which is not an integral domain. So the ideal generated by 4 is not prime. Well, so two different ways to go about solving the same question. More examples. Let's look at in Z bracket X. So in Z bracket X, the ideal generated by X is prime, but not maximal, as we saw earlier. And the reason now, right, let's just take the quotient approach. I mean, you could also verify it directly, but it's easier in this case just to say, hey, we already showed that this quotient right here, so let's put a colon here, the reason Z bracket X is isomorphic to Z, which is an integral domain, but not a field. Another example. So now let's work in Z3 bracket X. And what I want to do, so let's consider the ideal generated by the polynomial 1 plus x squared. And we can ask the question, is this ideal maximal? Is it prime? Well, okay, so here we go. So since 1 plus x squared is equal to 2 plus x quantities squared in Z3 bracket x. We have the ideal generated by 1 plus x squared is contained, properly contained, in the ideal generated by 2 plus x, which is properly contained in Z bracket x. So that tells us then that this ideal right here is not maximal. Since, so now if we look at 2 plus x squared, that's an element of this ideal, right, because they're equal. But 2 plus x is not in the ideal generated by 1 plus x squared. Now, why is that? Well, think about what elements in here look like. They are polynomials. They're the zero polynomial together with all polynomials that have this as a factor. I think it's just say all polynomials with 1 plus x squared as a factor. Which means if you're not the zero polynomial, then you have to have degree at least 2, which means that no degree 1 polynomial is going to live inside this ideal. So what does this tell us then? So conclusion, ideal generated by 1 plus x squared is not prime, or is it maximum? In fact, so one of those things we could deduce from the other, right? If it's not prime, which means that the quotient is not an integral domain, then it's definitely not a field. So if it's not prime, then it's definitely not maximal. And we can say it in the opposite direction. So let's say this as a corollary. 27.6. I'm going to actually say the converse of this, though. So let R be commutative, or I guess it's really the contrapositive, huh? Commutative with 1 if, or let's say, if I is maximal, then I is prime. Right? Why is that? Because when you take the quotient, right? I guess let's write up a little proof here. If I is maximal, then we know that the quotient R mod I is a field, which means that R mod I, every field is an integral domain. And so R mod I is an integral domain. Therefore, or thus, I is prime. Right? So maximal ideals are prime. Prime ideals are not necessarily maximal. Okay. Okay, this next result's kind of a technical result. So here's what I'm going to show. So let me say it like this. Our next goal, show that every so I guess it'll be at least how do I want to phrase this? Every ring with 1 / field has a familiar subring slash subfield, right? So this is kind of two statements rolled into one here. First, we have show that every ring with 1 has a familiar subring, and show that every field has a familiar subfield. And so we're going to need this fact right here. So let's say this is a theorem, so theorem 27.7. Let's let R be a ring with unity. Then the mapping phi from Z to R, defined by phi of 1, well, do I want to just define it with, yeah, no, I guess we can say phi of n, so let's just say where everybody goes. Phi of n equals n dot 1 is a homomorphism. Okay, so we just proved this by cranking it out. So let's look at phi of m plus n. That would mean m plus n dot 1. Right? So take 1 and add it to itself m plus n times. That's equal to, so let me write it out. It's equal to 1 plus blah, 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 plus 1, where there are m plus n of those. Well, just break it into two groups, right? So break it into a group of m of them and a group of n of them, right? And then that's going to be phi of m plus phi of n. Right, so it respects the additive property. And so also then, if we do phi of mn, okay, so that's going to be mn dot 1. So, yeah, how would we do that? So okay, let me do this in 2 steps. So first of all, what this means is add 1 to itself mn times. And then what we could do is break this into groups. Well, so how would we do that? We would take let's take n of them here. And break them into groups of n, and how many are you going to have total? You're going to have m groups. Right? So that's equal to m, how do I write that? Oh, right, no, so then, sorry, now we distribute, right? And so this is equal to 1 plus dot 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 plus 1, m of those times 1 dot dot dot, oh, 1 plus dot 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 plus 1, right? So there would be n of those, and so that will be phi of m times phi of n, right? So I'm applying the distributed property from here to here, right? For each of these ones, you're going to get a group of n ones, right? Multiply that out, and so if you wrap it back up, here's what or if you go from here to here, you're sort of undistributing, I think. Anyways, okay, so that's the that completes the proof. Okay, so yeah, let's finish off with you know, I think I'm going to stop right here, right? Because I want to combine the two, and it's a bit much. So I think what I'm going to do, I'll stop right here, and then we'll pick up with that, and we'll get to the punchline. Remember, the goal was to show that every ring with one / field has a familiar familiar subring. But there's a bit of work to do, so I think rather than pushing too far ahead, let's stop right there. All right, we'll see you.